Hello everyone, I'm Guanyu from Tsinghua University. It's an honor to be here to introduce our work, IMap, fast and scalable in network scanning with programmable switches. Let's start this talk with network scanning. Network scanning is a typical procedure to discover active hosts, ports, and services in the network. Currently, it has become a standard measurement technique to understand the security situations of the target network, even the entire internet. Recent studies showed that network scanning can help review new security vulnerabilities, detect vulnerable hosts, and monitor service deployment. Obviously, network scanner plays a crucial role in conducting such scanning. Today, more and more complex scanning tasks have created new requirements for network scanners. According to Siemens Monthly newsletter, since COVID-19, the frequency of cybercrime increased 300%. And another report from Improva indicates the duration of network attacks is getting shorter. This demonstrates that security incidents are occurring more and more frequently, and some of them occur in a very small time scale. As a consequence, network scanners should complete a comprehensive scanning as fast as possible. Otherwise, some important security incidents may be missed. Recently, IPv6 has been in the stage of large-scale adoption, which means increased address space. And along with the deployment of 5G networks, more and more IoT and mobile devices are connected online. Both of them lead to a much larger scanning space. It means a network scanner should be scalable enough to support current net scanning. However, today's network scanners cannot provide a timely security snapshot and keep pace with sovereign scanning space. A closer look into today's network scanners shows they are limited by two factors fundamentally. First, in terms of implementation targets, current network scanners are all implemented on commodity servers. As CPUs on servers are slow for packet processing, the scanning speed of the CPU-based scanners is intrinsically limited. Second, in terms of deployment locations, current network scanners are all located at the network edge, where the link has limited bandwidth but needs to sustain all the probe traffic. Besides, the long end-to-end scanning paths indicate more bandwidth waste for networks and larger possibilities of undesirable packet dropping. So how to address these limitations? We have a basic but effective idea. That is in network scanning, so that scanners can be implemented with high-performance switching ASICs and obtain the huge spare bandwidth and short scanning path from the in-network deployment. But is it possible? The answer is yes. We observe that programmable switches bring unprecedented opportunities to address those limitations. They are specialized for high-speed line-rate packet processing and can also be programmed with domain-specific languages like P4. More importantly, programmable switches provide unique vantage points to conduct in-network scanning. Therefore, we propose IMap, a fast and scalable in-network scanner with programmable switches. The usage of IMap is similar to traditional network scanners. First, operators should specify the scanning space, including the address list and the port range. Then, control plane programs pass these configurations and issue the parser parameters into the packet processing logics. After that, IMap data plane programs generate high-speed probe packets and process response packets accordingly. The scanning results, that is, the information extracted from the response packets, are written into a persistent database. Finally, operators can query the database to obtain scanning results. The core of IMap includes two models, which we will describe in detail later. Let's see the probe packet generation model first. The switch is designed to be a packet forwarding device, not a packet generation device, so we leverage a template-based mechanism to generate high-speed probe packets. First, the switch CPU prepares a set of template packets and ingests them into the switching ASICs. Then, the accelerator keeps looping these packets in the switch pipeline to achieve 100 Gbps. Some of the template packets will be sent to the replicator, which replicates the template packets into several switch ports. Finally, the editor modifies the headers of replicated template packets into desired probe packets. Nevertheless, to be a practical high-speed network scanner, IMap should cover the scanning space completely and adapt the scanning rate according to network conditions. In the high-speed scanning, simply probing IP addresses in numerical order would overwhelm target networks with scanning traffic. To avoid this, IMap should scan using a random permutation of the address space without duplications and omissions. However, the switching ASICs only have limited memory resources and programmability, which cannot support the address generation approach in CPU-based scanners. To save memories, we design a probe IP range PIPR table based on register arrays, and we also leverage the flexibility of the switch CPUs to supplement ASICs. The PIPR entry producer can generate a random computation of the probe IP ranges and fill them into the PIPR table in order. After that, probe packets can iterate through the PIPR table to obtain random destination IP addresses. When the scanning for the entire PIPR table is finished, the PIPR entry producer should fill a new round of probe IP ranges into the PIPR table. However, filling the PIPR table is a time-consuming task. It means after a round of scanning, we have to wait for the new filling to start the next round of scanning, which is inaccessible for IMap. To resolve this problem, we introduce two PIPR tables and a rolling filling mechanism. When one PIPR table is being scanned, like T1, the other PIPR table, T0, is being filled with the next round of probe IP ranges. Until now, the designs above only consider one port scenario, which should be extended to support a port range scenario. Since the address of probe packets already has good randomness, we choose to scan ports one by one. And because updating the port register from the control plane would bring about risk conditions, we design a port self-increment mechanism in the data plane. When the scanning address space is all scanned, the port register increases by 1. With all the mechanisms above, IMap can generate probe packets to cover the scanning space completely. To avoid affecting the network, IMap designs a network-aware method to generate high-speed probe packets with adaptive rate. The adaptive here has two kinds of meanings. First, the IMap data plane should have an accurate rate adjusting interface, so we add a throttle in the switch pipeline, which consists of two registers. The first one is a timer register, used to record the time from the last replicated template packet. The second one is a rate register, used to hold the expected time interval between replicated template packets. The register can be specified by the control plane. For every incoming template packet, we compare the values of the two registers. When the timer exceeds the rate, we pass the template packet to the replicator and reset the timer. Otherwise, we continue to recirculate the template packet. The second meaning of adaptive is that the IMap control plane should be aware of the network conditions. Thus, it should estimate the network conditions, then determine the scanning rate and update the rate register in the switch pipeline. To achieve the scanning as fast as possible, IMap needs to maximize the total scanning rate on all ports, but the actual load brought by IMap cannot overwhelm any link in the network. To solve this scanning rate adjustment problem, we formulate it with linear programming. For more details, please refer to our paper, and such adjustment should be repeated to adapt to routing dynamics when the routing tables in the scanning network change drastically. Then let's see the response packet processing model. As an in-network scanner, the input for IMap has both normal packets and response packets, so IMap should first distinguish them correctly. Normal packets will be forwarded according to the original forwarding model. Since the throughput of response packets may be large, IMap needs to efficiently process the response packets to avoid saturating the storage server. To distinguish response packets from normal packets, one approach is to maintain a single state for each probe packet. However, the switching ASICs only have limited memory. To resolve this, we design a seamless connection mechanism similar to sync cookies. We encode the single state into the mutable fields of each probe packet, and these fields also have recognizable effects on fields of the response packets. Especially for TCP SYNC scanning, the editor sets source port as the hash of key, proto, source IP, and destination IP, and then sets sequence number as another hash with source port and destination port. Accordingly, for received SYNC ACK key, IMap has a verifier that checks the destination port and ACK number to determine whether it is a valid response to the probe packet. One potential issue is that the switching ASICs only support fairly simple hash operations, so attackers may perform chosen plaintext attacks to restore the key, and deliberately inject forged response packets to pollute the scanning results. To reduce the damage caused by compromised secret keys, IMap updates the key periodically. However, simply updating the key would result in a missed key when the response packet arrives. For example, key 0 is used when IMap generates the probe packet, but after this packet is sent, key 0 is updated to key 1. Soon, the response packet arrives. The verifier determines this packet is invalid, as the current key cannot obtain a correct validation for its headers. To address this issue, IMap maintains 3 keys at any given time: the previous key, the current key, and the next key. Every t seconds, IMap rotates a slot index from 0 to 2, and that key, the current key, is used for the hash function. When IMap starts, the slot index is 0 and the current key is key 0. In the next t second, the slot index increases to 1, where the current key is key 1 and key 0 is the previous one. Then the slot index becomes to 2 and the current key becomes to key 2. Here, key 1 is the previous one and key 0 is to be updated. Next, the slot index rotates to 0 again, where key 0 is updated to key 3 and key 1 is to be updated, and so on. The editor will also encode the 2-bit slot index of the current key into the mutable fields of the probe packet. To avoid saturating the storage server, IMap desires an efficient response packet processing approach. One intuitive approach is to use hash mechanisms. However, as the key set in IMap is too large, this mechanism requiring GB memories is not feasible. Instead, IMap adopts a response packet aggregation mechanism. More specially, IMap designs a dedicated n-size register array to temporarily store the scanning results. During the scanning, the information extracted from the ith packet will be stored in the ith register. When the register array is filled up, the corresponding response packet carries all the results in the register array and goes to the storage server. Meanwhile, the counter is reset at 0 and another aggregation loop starts. For evaluation, we implement the prototype of IMap on a real physical to-final switch connected with a storage server, and our experiments are conducted with real-world deployments in our campus network. IMap adjusts its scanning rate according to the network conditions, which are obtained from the mounting system in our campus network. Due to security and reliability considerations, we are not allowed to replace the backbone switch with the IMap switch, so we deploy IMap with a release server to connect to one backbone switch in our campus network with the help of administrators. With the release server, we can collect and analyze the probe packets from IMap and the response packets to IMap. For overall effectiveness evaluation, this figure shows IMap can handle scanning at up to 55 Mbps without obvious heat rate degradation, which are thanks to the in-network deployment location and performance switch implementation. Note that 40 Gbps is not the upper limit of IMap. Instead, when we enable all ports of the switch, IMap can generate probe packets at a terabit line rate. And as shown in this figure, IMap gets much shorter round-trip response time for over 90% of hosts than state-of-the-art scanners. It demonstrates the advantage of IMap in employing in-network scanning. To validate the efficiency of the probe packet generation model, the first figure indicates the address randomization of IMap is good enough to avoid overwhelming the destination networks. Several virtual access networks in our campus network only receive thousands of probe packets per second. The second figure demonstrates that IMap updates the scanning rate every 10 seconds to adapt to the change of the network conditions. This is because the mounting system reports the campus network conditions every 10 seconds, and the LP problem can also be solved within seconds for our campus network. To evaluate the effectiveness of the response packet processing model, the left figure shows it takes about 4 seconds for high-end CPUs to reverse the real key using the stack algorithm. In this case, IMap is protected from chosen plaintext attacks with t smaller than 1.3 seconds and a common attacker. The right figure presents that the aggregation enables a 93.8% reduction in packet rate of scanning results for the storage server, which efficiently protects it from being saturated by massive response traffic. We have further done some analysis to scanning results to explore potential applications of IMap. We attempt to track the adoption of common protocols, and this table lists the top 10 open ports we observed in our campus network and reveals several interesting findings. Among the 10 ports, the ACE RPC and RDP catch our attention because they are known for information leakage. For instance, this figure is a screenshot from one of vulnerable RDP hosts, showing that attackers are allowed to perform shutdown operations on the RDP login screen. Considering the popularity of the two protocols, we investigated the exploitability of their vulnerabilities in our campus network, as shown in this table. We have also contacted our network administrators, and they confirmed these risks and issued a notice to remind teachers and students to check their configurations. There are also cases in our paper that reflect the potential of IMap in faster revealing security incidents with high-speed scanning. To conclude, we identify the limitations of current network scanners, propose a fast and scalable in-network scanner, IMap, implement its open-source prototype, and conduct extensive evaluations with it in our campus network. We hope IMap can serve as the foundation of next-generation terabit network scanners, and more efforts from the community can join us to fully realize this vision. That's all. Thank you. I'm happy to take any questions.